For this STAAR Test Algebra 1 review video, we will be going over the domain and range of a function and functions, what makes up a function, and what is considered non-functions. For this lesson, make sure you have paper, pencil, and calculator at the ready. There are going to be certain moments in the video where I highlight certain things, where I ask y'all to read certain parts or participate in doing the problems on your own. At those moments, I would like for y'all to pause the video, have your set of notes, and copy down and try to do those problems, or copy down the information to have at the ready and study before you take the test later on in the year. So just try to engage in as much of the material as possible so that you can pass the Algebra 1 STAAR test. We will not really need a calculator for this lesson because most of the content in this lesson is just memorizing certain facts about domain and range, being able to identify things on tables, graphs, and other different forms of or other different media that this information can be available to you. So you can skip the calculator part for right now for this lesson. If you would like to use it, fine, but largely we will not be using the calculator. All right, with that being said, let's continue on with the lesson. There are two specific TEKS we're going to be looking at for this lesson. TEKS being the bullet points to what you are required to learn for this course. A.6a, determine the domain and range of quadratic functions and represent the domain and range using inequalities. And A.2a, determine the domain and range of linear functions in mathematical problems. Determine reasonable domain and range values from real-world situations, both continuous and discrete, and represent domain and range using inequalities. Our goals for today's lesson. Today I will find domain and range so that I can determine the domain and range of linear and quadratic functions. I'll know I have when I can determine reasonable domain and range of real-world problems. So let's start off with domain and range. What do I mean when I ask you to find the domain and range of a function? So domain talks about x values. X values on a table, x values in a word problem, x values on a graph. Wherever those x values are located, I'm asking you to list those. What is the domain? What are all the possible values of x or other forms of the same thing that you can list and show me for this particular scenario? Okay, other ways you can say the x value is domain, input, independent, or somewhere that's on the horizontal axis. That's on a graph. Those are typically how you describe domain or x values. On the other end, you have y values. The range can also be called the y values, the output, the dependent variables, because typically y is dependent on x when we're talking about equations or relations. Vertical axis, which is the y-axis, is where you will also find all the y values on a graph. So all these different names all mean the same thing. I'm asking you to find the y values of a certain problem. So again, domain is all the possible x values of a function, whereas range is all the possible y values of a function. I'll give y'all some examples on how to find those in a bit, but so far this is the introductory. Domain is x, range is y. Domain is horizontal, range is vertical. Now, within domain and range, there's different types of graphs that we're going to see. So, continuous and discrete types of graphs, or scenarios, tables, etc. So, what are they? What is a discrete function? A discrete function is a set of input values that consists of only certain numbers in an interval. Okay, so it's not a list of all the numbers, it's a list of a certain segment of numbers. Okay, so for example, you see on this discrete function, this discrete number line, dots only on the number 1, 2, 3, 4, and 5. So our domain, or our discrete domain range, whatever this is called, will be just 1, 2, 3, 4, 5. Notice how it does not include anything in between these dots. So nothing like 1.5, 1.75, 3 or 3/4, or I'm sorry, 3 halves, whatever it is. Nothing between 1 and 2, nothing between 2 and 3, 4 and 5, etc. Just those numbers listed in the dots. And as you can see right here over on the right, the discrete representation of the graph, they are just dots on a graph. They are not connected. They are individual points that are not connected in any way, other than they're just on the same graph. So we would list each individual domain and range, each individual part of the domain and range. That is discrete. Now, continuous domain range is a set of input values that consists of all the numbers in an interval. So I want y'all to notice right here all the numbers from 1 to 5. So notice how 1 has a solid dot, and then we have a line that connects 1 all the way up to 5. So what this is saying is that all the numbers between 1 and 5, that includes 1.7, 1.8, 1.0000567, 2.3, 2.9, 3.2, all the numbers, square root of 5, whatever it is, they're all included from 1 to 5. And so the way we talk about continuous domain and range is if we use inequalities. So we describe the numbers between 1 and 5, and then these inequalities, depending on what we have for the dots and so on, will change. Depending on what we have for the dots, which I'll talk about in a little bit, these inequalities will change. But essentially, we're still talking about all the numbers between 1, and 5 for continuous domain and range in this example. And some examples of continuous graphs over here on the right, notice how we have a line that goes through everything. If we had any dots, it would be a line that just goes through it all. There aren't any breaks. And if there are breaks, we would talk about those breaks when we describe domain and range. But it is just a line that connects nearly everything. So some examples of what a discrete function would look like in the real world: number of eggs in a basket, number of kids in a class, number of Facebook likes. Y'all probably don't use Facebook at this point, so number of TikTok likes or comments or whatever. Number of diaper changes in a day, number of wins in a season, votes in an election, etc. Notice how all of these talk about just single numbers: 1, 2, 3, 4, 5, and so on. They may even include 1.5, 1.7, but they're all single numbers, single individual things that we would count in general. Continuous. Examples of continuous: weight difference to 8 decimals before and after cookie binge. So depending on exactly how many cookies you eat, they all can vary depending on the amount. You could eat an ounce, you could eat half an ounce, you could eat 2 ounces and or 2 pounds and 4 ounces, 2 pounds, 4 ounces, 4.5 ounces, and so on and so forth. The point is, there's a wide range of numbers in continuous. Wind speed, water temperature, volts, electricity, etc. So those are the differences between discrete and continuous. Okay, so let's go through some of these examples. If you want to try on your own, pause the video and see and pick which one you think it will be, the first, second, third, or fourth. But I'm going to go through this and explain what this is. So we want to know, for this table, what is the range of the table below. So what does range deal with? Range deals with y values. We want to know what the y values, or in other words, the output dependent, or whatever lands on the y-axis on a graph, the y values of the table that we see. Now, the next thing we need to know is this a discrete function or continuous? Because I want y'all to notice these four different answer choices. 2 of them are in the discrete form, of numbering, of explaining things, and the other two are in the continuous form of explaining things. So we need to determine whether this is a discrete or continuous function before we figure out. So, is this discrete or continuous? How do we tell? Well, all we're given is values on a table. Nothing is telling me that 0, 0 is connected to 1, 3, which is connected to 4, 7, or 6, 8. Nothing is telling me that any of these points are connected. I'm just given a table of values. So this tells me this is discrete. So discrete tells me that I'm going to be listing everything. Because I'm going to be listing everything, these inequalities don't make sense, because inequalities tell me everything between 0 and 6. Everything between 0 and 8. So, got to get those out of there. I only want specific numbers, specifically what's on the table. So now, next thing I need to know is range deals with y values. So which side of the table am I going to focus on to describe range? All the y values. So that means 0, 3, 7, and 8 are all the numbers for the range. Therefore, the first one doesn't make sense. The second one, the second answer choice is my answer for this. Okay, another example. What is the range of the graph below? So, again, pause this video if you want to try this before I explain it, but otherwise I'm going to continue. Range, what does that deal with? Range, we already said, deals with y values. So, what are the y values on a graph? Well, I need to figure that out. First thing I need to notice is whether this is discrete or continuous. Remember, discrete are just dots on a graph that aren't connected, or just individual points that have no connection to them. Continuous has a connection from one point to the other, a continuous line that connects them all. So what do I have for this graph? Do I have discrete or do I have continuous? None of these dots are connected through a line. So this is a discrete graph that I have. Now, why is that important? Look at one of your answer choices, the last one in particular. That is in terms of a continuous domain or range. So I don't want continuous. Inequalities means there's continuing things going on. I don't want it. Okay? The other three choices are my best bet. Now, how would I describe the range on a graph with a bunch of points? What do? Well, if you remember, these points have an x, y coordinate pair. So let's just start listing them. For the first point, I see -2, 4. So I have -2, 4. For the next point, I have 0, 3. For the next point, I have 3, -1. And then for the last point, I have 6, 7. So 6, 7. These points, like I said, are in terms of x, y. So what does range ask for? Ask for all the y values. My y values should consist of 4, 3, -1, and 7. Look through your answer choices. Which one is the only one that makes sense? The first one right here. Okay, -2, 0, 3, and 6. Those are all numbers that are on the x-axis. I don't want that. -1, -2, 0. Looks like it's listing all the numbers that we have, which we don't want all the numbers. We only care about the range. So those two are not my answer, and the first one is my answer. Just to go back and talk about domain for the previous two problems, the ones that we just did. If I were to ask you instead what is the domain of this problem, of this table, we would not look at the y values. We would still know that it's discrete. We would not look at the y values. We would look at the x values. 0, 1, 4, 6. those would be all my domain values if I were to ask you that. So the first one would be my answer. And for this problem we just did, if I were to ask you for the domain of the graph below, I would ask you for negative 2, 0, 3, 6. And so the second one would be my answer. So I just kind of wanted to give you all the domain view of those problems just to talk about it. But anyway, so let's continue on to the next part. What is the domain of the ordered pairs below? So we just got done talking about ordered pairs in the previous graph. What are ordered pairs? They are X, Y. They are pairs that you can graph, either put on a table or on a graph, and using the X, Y as a coordinate. Using the first one as the X, and then the second one as the Y. So these are all ordered pairs. It's asking us for the domain. What values do we care about when asked for domain? We care about the X values. So with each of these ordered pairs, they're all separated by 2 parentheses here. So this is the first ordered pair. My X value for that first ordered pair is negative 6. The next one is going to be negative 4, negative 2, 1, 3, and 4. One thing I did forget to mention, or did forget to ask y'all, is this a discrete or continuous function? It is not continuous. It is discrete because these are just individual pairs where we don't know there's a connection to it. They're all just listed individually. So this is what we would call a discrete function. Now that's important because, like we did with the previous problems, discrete means we're not going to be listing these as inequalities. So those 2 answers are gone. Instead, we're going to look at a list of numbers. And like I said, we're looking at the X values because we're looking for domain. So that means our X values, our domain, will be from the first answer right here. Now, if I were to ask you for the range, it would be all the Y values. So instead, you would see a different list. Your list would consist of, not in this order, could be in a different order, but 2, 5, negative 2, 5 again. We don't have to list it. We only have to say it once. 1 and negative 3. So that would mean the second answer would be for range if I were to ask you for that. But since I'm only talking about domain, this is my answer right here. Okay, now let's talk about continuous domain and range. This one's going to be challenging because there's going to be some rules that we're going to have to memorize and be aware of when looking for continuous domain and range. So before we get into all this, I want to draw a couple pictures for you. And I don't think it matters the color I'm sorry. One's going to be a circle and the other's going to be a square. So that these different things are going to be distinct. I'm going to draw a few faces here. So I'm going to draw some signs. May look familiar to you. And then on the other face, again, I'm going to draw some signs here that may look familiar to you. And I'm doing these certain creations on purpose here. Okay, let me zoom in a little bit. So this I would call solids, and this I would call dotted, dashed, or let me do this. Not solids. Let's call this a bunch of closed stuff, and let's call this all open stuff. Okay? So on a graph, you're going to be seeing certain things that's going to relate to certain symbols. So with solid dots, that's usually in reference to greater than or equals, or less than or equals. These signs that you're seeing right here, this is the less than or equal to, and this is the greater than or equal to. Okay? So less than or equal to, greater than or equal to are going to be used when you see solid lines or solid dots. Now, when you see open dots and dotted lines, these are usually going to mean less than or greater than. Notice how I did not say equal to. Okay, underneath these lines, these mean equal to. Okay, but without those lines, there's no equal. Dots open means it's empty, means you don't include whatever that dot or line is, or dashed line is covering. Okay, so with open, you're going to be using these symbols. With closed, you're going to be using these symbols right here. So I like to call the left side the snowman. I like to call the right the snowman face. The right side's the robot face, robo face. There's just something cutesy to kind of memorize what goes where. It doesn't matter. You can put the robot, the square on the left, the circle on the right. It doesn't matter. But just wanted to show y'all something to help memorize how to look at continuous domain and range. Okay? So, with that in mind, we are going to be looking at continuous domain and range. Now, we got different scenarios here. So, look at this first one here. We have open dots, we have solid lines, we have closed dots. And each one of these things are going to tell me certain ways to write my domain and range. So domain, let me zoom in a little bit. Move my face. So with domain, I'm looking for x's and y's. I'm sorry, x's. On the graph, that means I only care about the numbers that are related to the x-axis right here. So looking left and right, there's an endpoint to the left that I'm going to include in my domain. To the right, there's an endpoint that I'm going to include in my domain as well, positive 1. And again, I'm basing everything off of the x-axis right here. Now, the next thing I need to know is whether to include those dots or not, to include -3 or to include positive 1. Well, -3 is open, so that means there's going to be a less than symbol that I'm going to use. Positive 1 is closed because of that dot, so that means I'm going to be using a less than or equal to symbol. Remember, open and closed, those dots that I was showing y'all, the noses of each of these faces, tell me which sign I'm going to be using for domain and range. So, with domain, that dot is open, that dot is closed, and so I would write it the following way. -3 is less than x is less than or equal to 1, which is telling me everything between -3 and 1. 1 is included, -3 is not. That's how you read that. With range, this may get a little tricky, but bear with me here. With range, I'm looking at all the y values. So I'm looking up and down the y-axis. So up and down the y-axis for this graph only, which means I'm only looking for where this graph touches on the y-axis. So that's going to include the number 4, -4, at the bottom. And at the top, there's this peak right here, which looks like it's 0. And then it's also over here as well. That looks like it's 0 as well on the y-axis. So from here, from the top to bottom, it's 0 to -4, or -4 to 0. So now, next thing I need to know is whether these are open dots or closed dots. So at the bottom, I have a solid dot, and this is going to be important. There's a reason why I'm saying this, and a solid line. There's two parts where the y is located. Solid dot, solid line, -4, that's included. That's going to be a less than or equal to symbol. Now let's go to the top where 0 is. Solid line, empty dot, open dot. That open dot says 0 is not there, but then when we travel down the line, 0 is there. So if there is a number, that usually fills in the gap where it's missing. So 0 is solid, less than or equal to as well. So our range is going to be -4 is less than or equal to y is less than or equal to 0, which in layman's terms, all the numbers between -4 and 0 for the y-axis, including -4 and 0. So this is probably the hardest it's going to be. When you have a segment of a line that you have to get all the different domains and ranges, all the different parts of the domain and ranges for continuous. Okay. Now, let's talk about equations in general. There are rules for certain equations. So, for example, this is a quadratic equation. There are specific rules for quadratic equations, and especially for ones that go up, ones that go down, etc. Now, the domain, I want y'all to notice, look at this graph, look at all the way to the left and notice that there's an arrow. What does an arrow mean on a graph? It means it's going continuously all the way to the left. And then when we go for domain all the way to the right, again, we got another arrow. This arrow means we're going continuously to the right. So there's no gaps. There's nothing weird about this quadratic equation where I have to fill in the gaps. It's just everything is there. And so for domain, we say that all the real numbers are there. However, for range, from bottom to top, and again, I probably didn't say this before, but domain, we read from left to right. Range, we read from bottom to top. Think of like when you're crossing a road, you look left first, and then you look right. And then think of range as like a golf range when you're swinging your club. Imagine where the ball is at. The ball is at the bottom, and then when you hit it, it goes up. So range starts from the bottom, goes to the top. So notice where the vertex is at. That's going to be what you're going to associate your range from. So notice that the graph is going up. That means we're going to say y is greater than or equal to 0. If the graph was going downward, instead we would have said wherever that vertex is at, y is less than or equal to 0. Okay? So, that's quadratic equations. Quadratic equations, domain is always going to be real numbers. And then the range, you got to be specific with it. Okay, and then linear equations. So this next one, there's specific rules for linear equations too. Linear equations. From left to right, notice how the line continues all the way to the left, never stops, all the way to the right, never stops. And so we have all real numbers for domain. And then similarly, from the bottom, it continues, never stops. And then from the top, continues, never stops. And so range is also all real numbers. Now, what do linear equations look like? They look like y equals ax plus b. In other words, things like 2x plus 7, 5x minus 3, 2/3 x plus 1, or 0.5x. All these different equations are linear equations. What do quadratic equations look like? They look like functions like They're in the form ax squared plus bx plus c. These equations usually have like 2x squared, negative 5x squared plus 6, x squared minus 2x plus 1. You may even have x minus 3 in parentheses squared plus 7, whatever the form is. Okay, these are all considered quadratic when you see the square around the x. Okay, so that is domain and range with continuous. This one's going to be challenging. There's a lot of parts to it, but let's try to apply what we just learned into some problems here. So let's look at this example. What is the domain of the function below? And all we're given is an equation. Okay. Now, if you would like, if you want to know what the graph looks like, we can pull out Desmos. So with Desmos, just type the equation in, y equals 2x. Look at the graph, and there it is. And then as we zoom out, we notice that it just continues all the way to the left, all the way to the right. Never stops, okay? Now, we just learned linear equations, all the way to the left, all the way to the right. What is the domain of that? Never stops. So all those real numbers exist. First one doesn't make sense. Second one doesn't make sense. The last one, that's a discrete function. We don't want discrete. We want continuous. So another thing I forgot to mention, this is a continuous function. So that last one would have automatically gotten taken out of our answer pool. First two don't make sense because this linear equation, like we know about linear equations and like we just saw in Desmos' calculator, continues all the way to the left to the right. So there's no stopping point at either of these numbers. All real numbers is the domain for continuous. Okay, so here's a STAAR Test question for domain and range. A student rode a bike from school to a recreation center. The graph shows the student's distance in miles from the recreation center after riding the bike X minutes. What is the range of the function for this situation? So when asking for range, what parts of the graph are we talking about? We're talking about the y values. However, we need to be a little bit more descriptive here because we have a graph with different, that's described a little bit more than just simply y's and x's. So what are my y values? They're the distance in miles from the recreation center. Whereas the x's were times in minutes. So we're not talking about time. We're talking about distance. Okay? Now, how do we find range? Well, we start from the bottom and go to the top. So what are my numbers all the way at the bottom of this graph? They start right here. It looks like they start on the y-axis as 0. So somewhere, 0 has to be in my range. Where do they end? At the top. And we know they end because there's no arrows. They're solid dots. Where does it end at the top? It ends on the y-axis, 9. So we know that for the y values, it has to be between 0 and 9. Okay, what can we mark off automatically? So all the real numbers greater than or equal to 0 and less than or equal to 28. 28 doesn't make sense. So this one, take it out. 0 greater than or equal to 0 and less than or equal to 9. Okay, that makes sense so far. 0 and 9. All real numbers less than or equal to 28. We're not talking about 28 at all. All the real numbers less than or equal to 9. 9 is a part of our problem, so we'll keep that into consideration for right now. Okay. Now, let's read this a little bit more carefully. All the numbers greater than or equal to 0 and then less than or equal to 9. So greater than 0, meaning it starts at 0 and goes up, but then it stops at 9. So then it has to be less than or equal to 9. Greater than or equal to, less than or equal to. That makes sense so far. If we remember closed, if we remember our snowman and roboman, equal to is for solid dots and solid lines. So right now, this one makes sense. All real numbers less than or equal to 9. So all numbers less than or equal to 9. Okay, so we're good so far. But then according to that verbiage, less than or equal to 9 also includes everything below 0. But there is a clear stop right there. Therefore, this last one doesn't make sense. The only one that makes sense is this answer right here. Okay, let's look at another STAAR Test question. So, and apologize for the blurry image, but this is just how it came out. A florist is making a bouquet of flowers for a wedding. Each bouquet will have 9 flowers. The graph shows linear relationship between y, the number of flowers used, and x, the number of bouquets. The florist will use no more than 8 bouquets for the wedding. Which set best represents the domain of the function for this situation? There are some things in here that it tries to throw you off. The first part where it says linear. So there is a linear relationship, but notice how the dots are separated. So what type of function do we have? Do we have a discrete function or do we have a continuous function? And in here we have a discrete function because all the dots are separated on the graph. However, knowing this fact, we can't eliminate any of the choices. Notice how everything has been discretely stated. Individual numbers have been put into lists. So that doesn't really help us. So we got to move on to the next thing. So which set best represents the domain? So now we're looking for domain. Now we're only looking for no more than 8 bouquets. So does that matter? Let's count the dots. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's 9 bouquets. Actually, real quick, this does not matter really because all it asks is just what the domain is of the function. So what is the domain? Well, domain talks about all the x values. So all we care about are x values here. Now, this may be a little bit hard to read, but let's try and look what dots we have. So we got all the x values that we care about, the ones on the x-axis right here. So these dots, they have an associated x value that we need to figure out. So we have an x value of 0 for this first dot. We have 1 for this next one right here. Or you can list out the points as well instead of just labeling them. 2. We have 3. Notice how between 2 and 4 it's right in the middle, so that's 3. 4, 5, 6, 7, 8. Or if you would like, you can list all the individual points. So for this first point, this is 0, 0 for the first point. For the next one, that looks like it's halfway between 0 and 18, so that's 1, 9, 2, 18. For this next one, we have 3, 27, and so on and so forth. The point is, though, is you need to figure out how to identify all these x values. Okay? So make sure you understand where you're looking on the graph for those x values. I'm only looking at the x-axis. So which ones will list me all those x values from 0 to 8? Not these. Well, not the ones over here on the right, because notice these are all y values. So I don't care about range. I care about domain. Now I want to know what what best represents the domain of the function of this situation. What is going to tell me all the dots x values? Well, the only one that makes sense is this one right over here. This cuts out 1, 3, 5, 7, and so on. And this actually includes another number that's not a part of our domain, 10. So the only one that makes sense is this last one right here. And that's your answer. Okay, another example about domain and range. We have a part of a linear function is graphed on the grid, which inequalities best describe the domain and range of the parts shown. So now we have a line segment. We have a solid line. We have a couple dots. So first off, is this discrete or is this continuous? This is continuous. Okay, which means I'm not going to list my domain and range in individual numbers. There have to be inequalities that I'm going to have to create. So looking at the answer choices, that doesn't really help me. Everything is listed in continuous domain and range fashion. So let's move on to the next thing. Now I need to know what are my x values for domain and what are my y values for range. Let's start with the x values. So looking on the graph right here, all the way to the left, this point, and you can barely read it. I'm going to try to zoom in for y'all, and I apologize for the blurry line here. For the domain, all the way to the left, the x value is -7. All the way to the right, it stops right here. What is the x value for that? Well, that is 6. So for my domain, it has to be somewhere between -7 and 6. Before we do anything, let's look at our answer choices. So domain has to be between -7 and 6. Let's look at the first answer. Domain, -4 and 5. No good. Let's look at the next one. -7 and 6. Okay, that one's all right. Third one, -4 and 5 for domain. Again, no good. Domain, -7 and 6. Okay, so we whittled it down to 2 answers. Next part, let's look at the range. Okay, range starts at the bottom. So at the bottom of this line, we start from the bottom. Here's the dots. Range is looking at the y value. So I'm going to see what the connecting y value is going to be. And I see it's got to be -4. Okay, let's look at the connecting y value of the top of the line. And it's +5. Okay, so I know that for my range, it's got to be between -4 and +5. Okay, let's look at our answer choices. -4, 5, -4, 5. Okay, so we're good so far. Those are still the two choices. Let's go back to domain now. So domain, I notice, is a solid dot with no break in between and another solid dot. Now for solid dots, we had less than or equal to, greater than or equal to. Okay? With open dots, we had less thans or greater thans. We have solid dots for both, so that means -7 and 6 are both going to have less thans or equal tos with an x in between. Let's look at our answer choices. For this first one that I see on the left, -7 is less than x is less than 6. No good. So our only answer choice is this last one right here at the bottom right. Okay, and then if we do 5 and -4, we will notice that those are solid dots too, so those are also going to be less than or equal to for both. G of x is the same as y, so we don't have to worry about that, but either way, this is our final answer. All right, another example. A golfer hit a golf ball from a tee box. And I forgot, I'm supposed to be saying this for each one. Try and pause the video and see if you could pick an answer first before you hear my explanation. But anyways, let's just do that and then unpause the video when you get done and then continue on for the answer. Anyways, a golfer hit a golf ball from a tee box that is 6 yards above ground. The graph shows the height in yards of the golf ball above the ground as a quadratic function of x, the horizontal distance in yards of the golf ball from the tee box. What is the domain of the function for this situation? Okay, we know this is continuous, and none of the answers are in discrete form, so that's not going to help us. What will help us is figuring out what domain calls for. What is the domain? What do I want? I want x values. Let's look at our answer choices. Which ones involve x? The first one and the bottom right. The other two have y's in them. We don't want them. Okay. Now, which directions do I look for x's? I look left and right for all my x values. Okay. So I look all the way to the left. Here's a dot, a closed dot. The x value for that is 0. All the way to the right, here's another dot. What is the x value of that dot that is shown on the graph? 230. Okay, so that I know my domain has to be between 0 and 230. Okay, before we do that, let's just look at our answer choices. The first one, okay, that's still a good choice. Let's look at the last one, 6 and 230. No, 6 is talking about something else. So, the only one that makes sense without even having to figure out the less than or equal to symbols is the first one right here. And they would be less than or equal to symbols because those are solid dots. Solid dots. Okay, for this next question, we have just an equation. What is the range of y equals negative x squared minus 2x plus 3? So, this one's going to be a little bit trickier because we need to know what this looks like. However, we can eliminate 2 of these answers. If you would like, go ahead, pause the video, try this problem on your own before I give you all the answers, but I'm going to continue on either way. Range talks about which values, x's or y's. We're talking about y values here. There's 2 of these answers we can eliminate automatically. First one and the last one. Now, how do we determine which one of these it should be? Well, if you don't know, we can just graph it. Let's get the image. So let's graph y equals negative x squared minus 2x plus 3. And then make sure you get a good enough picture to see where this is at. Now I want you all to notice where this equation is and the orientation of it. Specifically where the vertex is, because you're going to base everything off of that vertex, the y value of that vertex. What is that y value of the vertex? It's 4, positive 4. So let's look at the answer choices. The only one that involves positive 4 is that third one right there. This one doesn't make sense. Now let's further clarify. The y values start at the bottom, but notice how the graph just keeps on going forever. It doesn't stop. But it does stop at the top, which is 4. So where's everything associated with the range? Everything is below that y value on the vertex, the corner. So how do we talk about range in terms of this quadratic equation? Well, everything is less than 4. Everything is below 4. So y has to be less than or equal to 4. How can you tell which one's less than and which one's greater than? Okay, I probably should have said this at the beginning, but hold out your left hand, make an L. That L stands for less than. That also looks like a less than symbol. So less than or equal to. Hold out your right hand, make an L. So that reverse L is your greater than symbol. Greater than or equal to. Left hand less than, right hand greater than. Easy way to remember which one is which. Either way, this is our answer for this STAAR question. Okay, just some things to kind of help you more visualize what you're supposed to be doing. For finding domain and range, algebraically, when you're doing all these different things, when you input x values, those x values that you input are your domain values. And any number that you get out, i.e. the answer from your calculator or from your calculations, those are your y values. Graphically, one way that you can think about finding the domain and range is drawing a box around the segment of the line that you're working with. This works with segments usually. Anything that continues on forever, not the best. However, anything that is a segment, this works for. So, draw a box around your graph. The x is the farthest left to the farthest right. That box is wrong, by the way. That line should be about right here. Anyways, farthest left to the farthest right. And then your y values are usually your lowest part of the graph to the highest part of the graph. And then you have usually written as an inequality, like the way you see here. Depending on certain things, it might have less than or equal to symbols. But graphically, this is how you would write it. For line segments, I should say. Tabularly, meaning like a table. Anything that's on the left of that table is usually your your input, your x values. Anything that's on the right is your y values. Okay, domain again is x's, range is y's. So, just some quick things to kind of think about when trying to find domain and range. Okay, let's very briefly talk about relation versus function. For a relation to be a function, there must be one and only one input for each output. In other words, the x values cannot repeat. On this example on the left with the check mark, we have 1 that maps over to p. We have 2 that maps over to q. 3 maps also to q. R doesn't get mapped to anything. Notice how 1, 2, and 3 all map to different, each individually can map to one thing on the right. That is a function. But let's look at something that's not considered a function. We have 1 that maps to p. We have 2 that maps to p and q. And we have 3 that maps to r. Okay, 2 is the problem here. 2 maps to 2 different things. 2 can only have one thing that it can map to. So therefore, that second example is not a function. So let's look at tables. Time. 0, 1, 2, 3, 4, 5. 0 goes to 0. 1 goes to 40. 2, 3, 4 also go to 40. 5 goes to 0. That's fine. Every single number is mapped to just one thing. And it doesn't matter if that one thing repeats. Okay, what's not a function? Time. 0, 0, 1, 18, 2, 36, 3, 54, 3, 84. So notice how 3 is labeled twice for 2 different numbers. That is not a function. So the second one is no good. Again, looking at another mapping. The left side of this mapping. Notice how each of these numbers has one single line that goes to different numbers. That's fine. The x values and the y values, all the x values have one thing that they map to. It doesn't matter if the y's repeat. It matters if the x's repeat. However, -5 being mapped to -8 and -2, no good. -5 has 2 different outputs, which does not make it a function. So this is not a function. All right, with that in mind, let's look at, we have more examples. There's also something called the vertical line test when you're looking at graphs. So What a vertical line test is you draw a line for every single part, or at least you imagine a line being drawn at every single part. At any point where the line passes twice through the line, it is not a function. So if we see here, this line that I drew passes once. Once. So this is considered a function through the vertical line test. Over here, if I draw a vertical line, it passes twice through this equation. Therefore, it is not a function. Okay, looking at a discrete function or a discrete set of graphs. If I pass through a line through each point and it passes once, then it is a function, which this is. However, over here, if I look through, there is one particular part where a line will pass through 2 points. This fails the vertical line test. Therefore, this is not a function. All right, now let's finally look at an example relating to functions and not a function. Is the relation below a function? Yes or no? How can we tell if there are functions? Well, in general, they cannot have more than one x value. They can have the same y value. However, the x value cannot be repeated. So let's look at all of these x values. Do you see any of them that are repeated? Yes or no? Yes, I see a few that are repeated. Well, no, just one set that are repeated. The 3's. Those are repeating. Because essentially what that's doing, let's see, -1, -9, and 3. And then we have 4, 5, 0, and -2. -1 goes to 5. -9 goes to 0. And then 3 goes to 4 and -2. So this is not considered a function. No, it is not a function. All right, so that's it for this lesson over domain and range, and then functions and not functions. If you have any questions, let your teacher know. If I'm your teacher, let me know. Otherwise, I will see y'all in the next video. Take it easy, everybody.